Hello and welcome to this final part on the monochromators and photodetectors in quantitative instrumental analytical chemistry. So here we'll be going back over monochromators, including the prism and reflection grating type monochromators. We'll be talking a little bit more in detail about how they work, especially with regards to the reflection, and we will be sort of going back over and revising a little bit on the prism type monochromators. As well as that, we'll be looking at photodetectors, which are transducers in our optical measurements. These are the things which are going to take the light which we have produced in our processes so far and translate those into electrical signals for our computerized detection systems, or even just in our analog detection and readout dials. So again, monochromators have 5 major parts. They have an entrance slit, they have a collimating lens, which is going to parallelize all of the light onto either the prism or the reflection grating. Then they're going to have the dispersion element, which is the reflection grating or the prism itself. So this is where we're going to see, in the case of the reflection grating, diffraction happening, which will enable the light of different wavelengths to be separated from each other. And then in the case of the prism, we will see refraction happening, wherein the light of different wavelengths will travel through the prism at different rates, and that will cause a dispersion of those wavelengths such that whenever we get through our focusing length or mirror and then focus that onto the focal plane of the exit slit, only the wavelength that we choose will actually be detected by our photodetectors. So again, a little bit on a refraction of a wave, and that's important for our prism gratings. So what's happening here is that as we pass our electromagnetic radiation or our light through different media, the degree or the direction of propagation will change based on the density changes of the media. So media 1, say, is air, and media 2, say, is glass. What we see is that air is going to be less dense than glass. And so our incident light passing here has quite a large angle with the normal, but that angle becomes more acute in the denser medium. So generally what happens is that we see a bend towards the normal, which is now 90 degrees to the interface. We see a change in angle which bends towards the normal whenever we are moving from less dense to more dense. However, if we're traveling in the opposite direction, i.e. from more dense to less dense, we see that there is a bend away from the normal. And so the extent of refraction is given by Snell's equation, which is based on the angles which are made with the normal. And remember that short wavelengths are going to be refracted more. So monochromators, as we saw last time, have 5 major components. They are also very useful to select wavelengths over a wide range. They make use of windows, slits, mirrors, lenses, and prisms or gratings to select wavelengths over a wide range. Monochromators usually have the following order of components. They have a slit to make a rectangular optical image, which will contain all of the wavelengths from our light. Then they will have a collimating lens or mirror to paralyze this radiation, because whenever it passes through the entrance slit, it will be refracted out of this slit, which will then cause a dispersion of our light beam. But by using our mirror or our collimating lens, we can parallelize that so that it can be directed directly onto our monochromating medium, which in the case of a Cerny-Turner grating monochromator is going to be a reflection grating. In the case of a Bunsen prism monochromator, yes, that Bunsen, we use a prism. Now, this is the older style. It's much cheaper, but generally with advances in technology and more widely available reflection gratings have kind of overtaken prisms, simply because they're generally a little bit more easier to use, and they generally have a wider applicability. So as I said, we have this collimating lens or mirror, which will create parallel beams of light, which can be directed onto our dispersing medium. So again, in the Cerny-Turner grating monochromator, this is a reflection grating. In the case of the Bunsen prism monochromator, this is a prism. So then we have a refocusing element after that, which is our focusing lens or our concave mirror in the case of this grating monochromator. These will focus the light onto the focal plane, which is where the exit slit is located in both types of monochromator. These exit slits then can be moved to enable the choice of a particular wavelength. Prism disperses by refraction at the surface interface, and grating disperses by diffraction at the reflective surface. So Bunsen prism monochromators. So many older instruments make use of these type of prisms that work by refraction of the light as it passes through. Diffraction gratings then, so these are the ones that we'll be particularly dealing with today. So what happens here is the diffraction gratings work in a similar way to the double slit experiment. So what's happening is we have parallel beams of light coming in, and then based on their reflection off of a surface, they will, and the sort of like the length of this, they will be reflected in all directions, and based on their wavelengths, they will be reflected at different angles. So if a small aperture hole can diffract light, then so too light reflected from an adequately fine sawtooth surface can also be diffracted. So these kind of levels or layers or grooves, as they're actually called, these are what are going to be very, very, very small, like you're talking nanometer scale here, and they are going to cause a diffraction in a similar way to the slit experiment caused it. So if we recall that light coming in to our diffraction grating, it would pass through this tiny slit and instead go from parallel waves to these spherical waves. So these are the components, as we saw before, of a Cerny-Turner grating type monochromator. So we have light, which includes both wavelength 1 and wavelength 2. So this is a combination of the two, are these dark blue lines. They pass through the entrance slit where they are diffracted together onto the concave mirrors. Then they will pass along they will be directed onto the reflection grating, which will reflect the light, but based on the fact that the grooves on this sawtooth reflection grating are very, very narrow and very, very small, what will happen is that we will diffract the light differently depending on the wavelength. Then these will be incident on a mirror again, and this mirror will then focus the light onto the focal plane, and based on the position of this exit slit, so for example, we want wavelength 2, we would position the exit slit so that it would be over this wavelength. If we wanted wavelength 1, we would move the exit slit such that we get wavelength 1. Could also move some of the internal components as well to sort of focus different parts of the beam on the exit slit. Diffraction gratings then work like this. So most modern instruments make use of diffraction gratings, and the extra path length traveled by wave 2 must be n lambda for constructive interference to occur. And again, we have this variation of Bragg's law. So n lambda is equal to d sine theta I, which is the incident light, so that's the light coming in, plus sine theta r, which is the reflected light coming out. So here we have the schematic on the right-hand side. We have our sawtooth diffraction grating. So we have incident beams of light here. We have beam 1, beam 2, beam 3, and these are all monochromatic beams at incident angle I. So I is the angle of the incident beam to the grating normal, which is here. And then the reflected light has another angle, which is theta R. So theta I is incoming here on this point, and then it is reflected with an angle theta R to the normal. Now, if the different beams, beam 1, 2, and 3, are going to interact constructively, then the extra distance traveled, i.e. C to D, so C to B to D, must be some integer wavelength multiple of the wavelength. So if, for example, it's only 1.5 of the wavelength, we will end up with destructive interference, and this will weaken the beam light, and so that helps us with regards to our wavelength discrimination. So how do we calculate D, or the grating width? So if we, for example, we have 2000 grooves per 1 millimeter, then D would be equal to 1 millimeter has 2000 grooves. So that means that since 1 millimeter is 1 million nanometers, then it's 1 million nanometers divided by 2,000 grooves, which means that there are 500 nanometers per groove. So that would be D for that particular instance. So then how do we do calculations with regards to our diffraction grading? So we want to know what the first, second, and third order wavelengths from our diffraction grading will be based on an incident angle of 30 degrees, a reflected angle of 45 degrees, and a grading which has got 2,000 lines per millimeter. We already saw how we get D for our equation a moment ago. So n, which is the integer, so it's for first order it will be 1, for second order it will be 2, and for third order it will be 3. So we weren't actually asked in the question how many orders to go to, but we'll just go to 3 for this instance. So this is our equation, which is based on Bragg's law of diffraction. So we have here that 1 millimeter for every 2,000 grooves. So sine 30 degrees theta, or sorry, sine theta I is sine 30 degrees because we were given theta I as 30 degrees here, plus sine 45 degrees. So if we put these into our calculator and work it out, we will find that we have 6.03 times 10 to the minus 7 meters, or 603 nanometers as our first order wavelength, which will be the most intense light. Second order and third order wavelengths then will be similar equations, but in this case, n will change. So here we have n lambda, but since n is equal to 1 for first order, so first order, so n is equal to 1. But in this case, for second order, n is equal to 2, so it's actually 2 lambda. Then we have to divide through by this 2 here. And then for third order, it's 3 lambda is equal to 603 nanometers. So that's going to be 603 divided by 3, which gives us 201 nanometers. So that's how we would do this calculation if we were asked to, for example, the major light is the first order light. So say, for example, we were asked what is going to be our first order light. That would be it's going to be sort of like the one where n is equal to 1. So diffraction gratings here again. So we have incident broadband radiation, which has got a incident angle and a reflected angle here. So we have our diffraction grating here. We have our grating normal, which is 90 degrees to our diffraction grating's base plate. So we have first order, second order, and so on. Reflection. So first order is usually the most intense. It's the major light. We usually only want first order diffraction actually. And so we use filters to remove higher orders, and glass can remove lines below 350 nanometers since glass is pretty good at absorbing UV light. So this is sort of like our first order wavelength here is 300 nanometers. For the second order diffraction, we have weaker incident light, weaker separated light. So the quality of monochromators. So spectral purity, scattered or stray light in the exit beam can affect the output. You know, we can end up with, because our transducers don't really discriminate that much about like what wavelength of light they're getting, so long as they're getting light, it can mean that if we have stray light inside of the monochromator, which passes through the exit slit, it can sort of cause aberrations in our data. So we use entrance and exit windows, dust and light tight housing. We coat the interior with light absorbing paint. So basically that means that any stray light which is not being processed by the monochromator or which leaks out, I guess, will be absorbed by the housing, which is painted to absorb the light, which means that instead of it being reflected around and doing crazy things, it just gets absorbed and that's it. We also need to make sure that there's no dust inside, because dust can get into the beam of light and can cause strange optical effects. So it needs to be light and dust tight. So usually you have a positive atmosphere in the inside of the instrument or inside of the room that the instrument is located in. This positive atmosphere means that all dust is pushed out. So dispersion ability to separate small wavelength differences. So linear dispersion, or the reciprocal linear dispersion, is the variation in L across the focal length plane. So what we see here is the dispersion ability here is going to be equal to the distance from the screen over the change in the distance from the screen over the change in the wavelength. So the linear dispersion is then the reciprocal of that, so d to the -1. So that's going to be the rate of change of the wavelength over the distance from the screen. It's going to be equal to d, which is the grading order. So we learned about that earlier. That was sort of like 2,000 grooves per millimeter, over n, which is the order, times f, which is the focal length. So focal lengths are seen here. So say we have this focusing lens, we have two parallel beams. They can be focused on a focal point f, which is at a distance f from the what do you call this? From the lens. So this point here is usually like the screen, which is y. So light gathering is the light collection efficiency of our monochromator. So we use this to improve signal to noise ratio, and radiant energy that reaches the detector should be as large as possible. So the light gathering power of an optical device increases as the inverse square of the f number. So that means that an f2 lens gathers 4 times more light than an f4 lens. Because of this process, that the light gathering power of an optical device increases as the inverse square of the f number. So the f number is going to be f is equal to f of the collimating mirror, so it's the focal point, over the diameter of the collimating mirror. Or it can also be the lens. That's also okay. Just whatever collimating device you're using. And so it's important that the amount of energy that reaches the detector or the transducer at the end be as large as possible. And then the spectral bandwidth is also important. So the range of wavelengths exiting the monochromator. So this is related to dispersion and entrance exit slit widths, which we will talk about shortly. So the effective bandwidth is equal to the bandwidth over 2. And that's basically related to the intensity of the light. And then that's going to be equal to delta lambda over delta y, which is the same as the reciprocal of the dispersion. So the effect of the slit width can have a big effect on the detector and how it detects the light. So the slit width can be changed to be more narrow or to be wider. And so the wider it is means that you will get more light exiting the monochromator. But the problem is that you also run the risk of potentially increasing the amount of different wavelengths which can exit the monochromator, which means that you end up with potentially more light. Well, it means you get more light at your transducer, which means that you get a higher signal, which means you have less problems with like too little light being absorbed by the transducer. So moving the exit slit allows for selection of different wavelengths. The bandwidth is the number of wavelength settings that can map the exit image to the entrance image. So here we have a schematic. So we have the total bandwidth here, which is this blue line here, but the effective bandwidth is here. It's only half of that. So if we choose the effective bandwidth, that means we're only really getting wavelength number 2. We're cutting out wavelength number 1 and wavelength number 3. However, if we were to widen the slit, we could in fact end up getting a little bit of leakage of wavelength 1 and wavelength 3 coming out. So it's important that we know the effective bandwidth and we choose our exit slit width dependent on that. So the slit width and the effect on the spectra. So if we have, this is the widest slit width, and if we have narrowing of slit widths, we can see what is happening. So as we make the slit narrower and narrower, we're getting better and better resolution. However, we are also changing the radiant power and the amount of energy which is going to be detected by the transducer. So complete resolution of two features is only possible when the slit is adjusted to produce effective bandwidth half or less of the difference between the wavelengths. So here we have three wavelengths, 1, 2, and 3, and that's their effective bandwidths here. So at exit slit 4, we're just seeing a kind of a continuum. We're not really seeing any peaks because of the overlap of the different bandwidth. So you can see here that there is an overlap here and here, which causes the peak to be here. There's an overlap here and here, which causes the peak to be here, which means that we just see a continuum and we don't see where our peak actually is. Now, if we make the slit narrower so that we're cutting out more of the effective bandwidth, what we see is that the peaks start to appear. However, there's still a lot of overlap. So the last thing is that we make it even more narrow so that it's now only half of the effective bandwidth at the start. So this is the effective bandwidth here. So now we've made it half of this original effective bandwidth. And so now we have very well defined peaks. And so we are getting a good picture of the wavelength 1, wavelength 2, and wavelength 3 positions, all based on the slit width and how that affects our optical image at the end, which is coming to our transducer. So now that we figured out how we choose what light we want, we need to have a look at our sample and how our sample is going to be measured. So sample containers and optics. So typically we have cuvettes of some sort. They can be the type that you may be familiar with, where there's an opening at the top. They're kind of like a cube shape. And then you pour your liquid inside or whatever it is you're going to measure. They can also be sealed tubes, which are used for gas samples. There are many different ways that, or they can even be two pieces of glass between which your sample is sandwiched. There are many different ways to contain the sample. Of course, we also need to be considering our lenses, our prisms, our gratings, and our filters. So made of a suitable material. So it depends what we're trying to measure, what we need to choose. So glass is pretty good for visible and near IR measurements. It's very bad for UV measurements because it absorbs UV light, which is just pretty good for us. It means that whenever we're indoors, we're pretty safe from UV rays of the sun. Silica quartz is good for UV up to near IR. The problem is silica and quartz are much more expensive than glass. And then sodium chloride is by far the best, has the widest range. But as we've talked before, it's not suitable for aqueous samples. It cannot be used in high humidity environments. It's difficult to handle. You can't really touch it with your fingers. It's very delicate, but it is very, very powerful as a tool for measuring like organic samples or anything really that won't interact with the sodium chloride. So here is a look at the sort of a commercial company's different sample containers, so, and how they have different transmissions over different ranges. So if we look here, optical glass, which is used for a lot of visible measurements, you can see here that below 300, it transmits 0% of light, but above 300, it transmits pretty well, up to almost 85% of the light, and then even transmits up into the IR region, although you can see here that there's a big drop off. Things like their commercial supersil, which is a form of silicate, they also have very good and really wide optical ranges, optical windows. So we call this a window where the transmission is very high, and so lots of light will pass through. So it can be used all the way from UV all the way up through most of the IR region, except for maybe around about the sort of OH stretch of water region. So it's not really good for water, but like anything in like the organic range, or you're looking at amides or carboxylic acids, it's all going to be good. So silica glass, good to about 350 to 2000 nanometers visible and near IR. Quartz and fused silica, good to about 190 nanometers UV and visible. Plastics, visible only. And solvent choice is important here, because if we have a solvent which is going to dissolve our sample, then we're going to have a big, big problem. Like if we put an organic solvent into our plastic cuvette is going to get degraded pretty quickly. Our sample is going to be ruined and our measurement is going to be meaningless. Here's some of the different types of cuvette types. We've got like the cuvette here, which has got a really long path length. So that's whenever we've got a very dilute solution. Remember back to the Beer-Lambert law, it's dependent on, the absorption is dependent on the path length, because the longer the light passes through the sample, the more chance there is for the light to interact with an analyte molecule or species. We've got the kind of regular one here with a nice little stopper on the top. Some have screw type stoppers. Some just have very just sit on stoppers. Usually this type are the best. These ones here are very thin or very short path lengths. They're good for highly concentrated samples so that you don't overwhelm your transducer. Got different ones here with darkened walls so that you don't end up with leakage and things like that. It's narrower here, but still wide. Various different types that are possible. So radiation transducers then, so how do we detect, after it's passed through our sample, how do we detect the light? Ideally, our radiation transducers will have high sensitivity, low noise, wide wavelength responses. They'll have a linear output, which means that the signal is proportional to the intensity of the light, which is incident on the transducer, and they'll have a low dark current. So that means they'll have a low current when the intensity is equal to 0. So the signal is equal to Ki plus Kd, where D is like the dark current. This is important. These two are kind of, low dark current and low noise are a little bit related. Low noise is this idea that whenever there's no measurement going on, or when the measurement is going on, it's not going to be overly affected by any sort of background things. Like it's not going to be affected by the temperature or vibrations. It shouldn't be affected too much by humidity or quantum effects and things like that. It should have high sensitivity, which means that even low intensity light can be detected. Wide wavelength response just really is important because you want it to be useful in multiple different ranges. You don't want it just to be useful in visible. If it's a UV vis spectrometer, you want it to be useful across the full UV and visible spectrum. So you want it to at least cover 200 to about 700 nanometers reliably. Linear output, this is important so that you have like the ability to make a calibration curve. A low dark current, which means that there aren't like spurious detections even when the current is low. So that means that it's kind of related to the noise. Basically, it means that the circuit doesn't randomly measure signal whenever it shouldn't. So there's sort of 6 major types. We'll mostly look at a couple here. So radiation transducer, they convert radiation from electromagnetic radiation to an electrical signal, and dark currents are common. And so this is a signal without radiation. Then typical phototransducers are here. They're photovoltaic cells, which are also sort of used for solar cells. There are phototubes, there's photomultiplier tubes, which are PMTs. There are photoconductivity transducers, silicon photodiodes, and charge transfer transducers. So the 3 that we're going to look at are these photomultiplier tubes, these PMTs. They're basically the same as phototubes. They're just a more advanced form, which has improved the sensitivity of our measurements. Then we have silicon photodiodes. We have charge transfer transducers as well. So here is a little bit of a description of these. So a photovoltaic cells, the photon generates a current at the interface of the semiconductor and metal. So photovoltaic cells have like a metal backplate, and then they have a semiconductor material on the top. And so the interaction of the photon with the semiconductor causes the electron to cross the band gap, which creates conduction, which then is conducted through the metal. And then that can be passed through the circuit and then detected by our whatever components in our circuit will detect the current. Phototubes then, so here, this is where the photon causes emission of electrons from a photosensitive solid surface. So what happens is the photon is incident on maybe a piece of metal. Whenever it hits that piece of metal, an electron is released or ejected from the surface, and then this electron is how the current is passed through and how the light is detected. Photomultiplier tubes are kind of based on phototubes, but they're more advanced. So we'll talk about that in the next couple of slides. Photoconductivity transducers. So here the photons are absorbed by a semiconductor, which produces electrons and holes, enhancing conductivity. Later on in this course, we'll talk more about semiconductors to an extent, although you've probably already met them. Silicon photodiodes, so photons create electron hole pairs across a reverse biased PN junction. We'll talk again more about those as we go through here. And then charge transfer transducers, so photons absorbed by silicon crystals create charges that are then measured. So photomultiplier tubes here. So here we have a photomultiplier tube on the right-hand side. We have radiation light coming in here, which is where our incident light is. And then this is going to cause a cascade of electrons to be formed, which will amplify the energy of the light so that it's more easily measured. So these are suited to low power radiation. You cannot use high intensity light with these because of the way that they multiply the power of the light. If the incident light is too powerful, then you're going to get too many electrons and you're going to end up with just destroying your photomultiplier tube, which is generally pretty expensive. So these are similar to phototubes, but with dinodes. So this means dinodes are just extra electrodes. So we have a photocathode, gallium arsenic, which emits electrons when irradiated. So here we have the radiation coming in. So remember that radiation has an energy which is equal to HV. So you'll often see H nu, you'll often see H nu written. Just that means that light. It basically just means light. Electromagnetic radiation. H nu is the same thing as light. So the photocathode emits electrons when irradiated. So we have the radiation light, which is incident on the photoemissive cathode. So this cathode is the gallium arsenic, which will emit electrons. So these electrons are then accelerated towards dynode number 1, which is more positive than the cathode. So it will kind of attract the electrons towards it. Then whenever it hits this point, what's going to happen is that we're going to see a creation of more electrons. So we're going to get these pass through each of the dinodes, and every time it reaches a dynode, it produces more electrons. And so eventually we end up with a huge number of electrons, which for every photon have produced around about 10 to the 7, so around about 10 million photons. Between 1 million and 10 million electrons have been produced for each photon of light, which is why if you've got a lot of photons of light, you're going to end up with a ridiculous number of electrons, which is just going to overload your photomultiplier tube and totally destroy it. So PMTs have very large dark currents, but this can be eliminated by cooling them to minus 30 degrees Celsius. So typically that's what happens. Typically it's cooled down by some sort of chiller to minus 30 degrees Celsius. So it's usually a heat exchange plate, which is then cooled by some glycol cooler. Okay, so let's check our comprehension. So what is the major wavelength of light that is produced from a monochromator where the grating is 3000 grooves per millimeter when the incident light angle and the reflective light angle are 30 degrees? So pause for more time if you need it. Have a little think about this, and then we'll go through it together in a moment. Okay, again, pause if you need more time. We're going to go through it now. So this is to do with a diffraction grating type monochromator. So we recall our Bragg's law equation where n lambda is equal to d sine theta of the incident light plus sine theta of the reflected light. So we're talking here about the major wavelength. So that means that we're looking only at n is equal to 1, the first order diffraction. So that means that we can fill in our equation. So lambda, well, 1 times lambda, we've omitted the 1 here because n is equal to 1. So that's going to be 1 millimeter over 3,000 grooves times the sine 30 degrees plus sine 30 degrees, which is a half plus a half, so that becomes 1. So that means that the wavelength here is going to be equal to 3.3 times 10 to the minus 4 millimeters, or 330 nanometers. So that would be how we would determine the wavelength of the major light that is produced from a monochromator, where the grating is that and the incident angles are those. So thank you for watching this. Check out the next session. Thank you. Bye-bye.